So mostly what I'm going to talk about today is scientific cyber infrastructure, in the NCSA building. And I've done a lot of work in this area. I started out my career though in the military, started out at a big 3-letter agency and then spent a lot of time at a big internet service provider. And as the internet's evolved, you'll notice that, well, I always make this analogy about cat videos and Netflix. YouTube cat videos as of 2021, 26 billion views. We made the internet really easy for entertainment and cat views and fun things, which is a good thing, right? But if you've worked, and many of you I see are younger, if you've worked in science, as many of us have, or scientific cyber infrastructure, getting the internet to do good things for science is really, really awful. And I'm going to tell you why. So the internet isn't really made for science. So one of the things I'm trying to do in my project, which is called Fabric, is we're building a test bed. We're trying to make the internet better in general, but in particular, the area that I focus on is to make the internet better for science. So I'll talk about in general why the internet's terrible, why test beds are important to think about how to make the internet better. I'm going to talk about 2 projects that are kind of intertwined, Fabric and Fab, and then talk about a little bit about our initial science use cases. So the internet is terrible for a lot of reasons. My background is mostly in networking and cryptography. And even as a casual user of the internet, and there's a great paper I will refer to called Toward a Theory of Harms in the Internet Ecosystem. It's written by David Clark and Casey Claffey. Both of them are the Internet Hall of Fame. David Clark is one of the original kind of godfathers of the internet. And they took another look in 2019 of all the kind of harms on the internet. But we know that routing is not good if you work in internet routing. There's a lot of bottlenecks these days. You'll notice more censorship, more disinformation. The internet is not resilient, even in the US, where it seems like we have lots of different providers. So there's not a lot of resilience. There's a lot of data collection, many times without your consent. There's a lot of reasons in general the internet is not a great place.
But in that context, what does harms mean? Anything not intended or? Yeah,
so harms, this inventory of harms includes things like it's not affordable for some people. It's harming you because it's not private. There's data collected. So harms in general, economic, geopolitical, kind of the catalog of harms. I focus more on kind of the technical harms.
Okay.
Let's need to sit these things.
Yep.
Get comfortable. So this is a chart here again. So for University of Illinois, most universities and most colleges in this country connect to something called Internet 2. And Internet 2 is a research and education network. Something that's really interesting that, so this is a snapshot of this past week of traffic on this research and education network. And that's really, research and education network really carries science traffic, campus traffic. Commodity is what carries your cat videos and Netflix. If you look at this here, the green, so this is Internet 2, which is the large kind of science and education network in the US. The green is kind of your science and research and education traffic. The rest is what I would call your cat videos and Netflix type stuff. And that's like at a typical campus. Meaning most of our traffic, much of how we design the internet and technology for networking is really based on entertainment, not science. That's a problem, obviously.
This is UIUC do that?
This is in total of Internet 2. So this is also Internet 2 connects pretty much all campuses. So this is just the aggregate of all campuses. Yeah. Each campus differs a little bit. Some of them are up to 80, 90% kind of Netflix, entertainment, YouTube, which is commodity and not the science and that type of stuff. Yeah.
Why is that inherently a problem that people use the internet for entertainment over science?
It's not inherently a problem. What becomes a problem is that the engineering and the routing and the protocols are really designed more for entertainment, and investments in innovation are more geared for the entertainment aspect, not the science.
Mm-hmm.
That's not bad for us as humans, but it's bad for us as scientists.
Mm-hmm.
So part of what we want to do is to reimagine a good internet, one that's private, that's secure, routing protocols that are flexible. We also want to talk about having compute and storage and networking throughout the network, not just, now it's kind of a tiered, place where different things happen at specific places.
All
Your presentation without a glitch, so.
It's coming
There you
in.
go.
Yeah,
Can you, I think, you need to put it back
I think
to,
I think it's not.
Video.
you see which one's selected. I just hit the arrow.
Is that online? Is it okay? Can you give a?
Srini, is that, are we back?
Yeah.
Okay, cool.
I'm gonna stay put. Okay, I'll just stay put. So this is a history of. So when you want to reimagine this new better internet, you don't want to necessarily do it on the live internet. You want to use a test bed to create it. So there's been a long, long history, and this is like a terrible eye chart, I realize, but there's a long history of mostly NSF, some Department of Defense investments in test beds. These are primarily kind of computer science test beds. Deter is a security one. Others are meant specifically around, say, cloud. Chameleon, for example, is meant to be kind of a bare metal cloud test bed. Others are more geared towards wireless or 5G or optical. So lots of test beds exist. The problem with this is when you try to reimagine kind of a comprehensive internet that takes into account everything from IoT to storage to data, is these are their own separate little verticals, and they've evolved and they kind of get deprecated, and then NSF doesn't fund them. So where do we go from here? So we are Fabric. I'm going to talk about that. Fabric is kind of Gen 4. And that's what I'm going to talk about today. So
In your, when you're thinking of this, are you thinking of like infrastructure in the ground, or, infrastructure or software and
Both.
protocols? Okay.
and that's kind of the value add of Fabric.
Okay.
So what is it? Fabric's really two projects. It's a terrible acronym that, just use the word Fabric. Science loves these terrible acronyms, but it's really two projects. One is this large scale test bed that's comprehensive around the US. There's 29 sites, all the way to your question, all the way from optical, all the way up to software. So we rely heavily on the Department of Energy. They have a network called ESNet. We heavily rely on some fiber from ESNet. So literally from the optical layer on up, you can do experimentation. Because we don't want to just build a test bed for ourselves, because we're not scientists, we relied when we made our pitch to NSF, what are really the design drivers, the science use cases? And I'll talk about a couple of those. An interrelated project is FAB, and I'm the PI for FAB. FAB is just the international expansion, but we're going to 4 additional places because there are additional challenges when you go transatlantic or transpacific with communication, everything from bandwidth to submarine cables to routing, all sorts of things like that. This is a leadership team. Primarily, it's these folks. It's a pretty big team. Again, we do rely on Department of Energy a lot for the optical layer. And there is a node, and there's a Fabric node in this building too. NCSA is a big Fabric node. So we were funded to do the first 4 years. We are just starting year 4 next month. So NSF funded us to actually construct this test bed. It's a very long process. It entails buying equipment, writing software. I'll talk a little bit about that, but just deploying, as you can imagine, 29 sites during COVID, supply chain issues, getting stuff in data centers, that's a long process. So that is about a 4-year process. After year 4, so after starting next fall, we will be in operations, full operations. So now we're kind of the early experimenters who are kind of helping us work through the kinks and things. So why Fabric? If you're wondering what, I still don't know what you're talking about. What is this Fabric? So because you saw those slivers of, kind of vertical test beds that not everybody was able to get to, a team of us proposed to NSF. We said, there's now the compute and storage is much cheaper than it has been back in the day when storage was very dear. If all that's cheaper, as there's more, GPUs are cheaper, FPGAs, all the compute kind of stuff is cheaper, how could we reimagine network architecture? So right now you go your endpoint, to a data center, to another data center, and it's a very tiered model. You know that it's going to go from here to there. Your endpoint, your laptop's here, the compute is maybe somewhere else, the storage is somewhere else. But what if we were to think about computing all along the path so that it wasn't just from here to there that it might compute? And this is really relevant for science. We collect things off an instrument like a telescope, we send it here, we do some processing here. That's not going to scale anymore. So we proposed, what if you were to reimagine so that it wasn't just routing done in one place, you could all along the path do routing, machine learning, things that you can only do in certain places today. We want to use, in other words, a network as kind of this big data instrument where we can do real-time measurements, so timestamping, let's just talk about, more real-time inferencing, so you don't have to draw everything back. And of course, with now a lot of new kind of science distributed applications, IoT, this presents a really good opportunity for us. So what is Fabric? You saw why we are doing it, but what exactly is it? Well, it's a nationwide network. So now it's international. So we have 29 sites in the US, 4 overseas, with compute and storage at each node. So in the NCSA building, we have actually a pretty large, pretty substantial Fabric node. Each Fabric node has storage, it has compute, it has software. Almost we have GPUs everywhere. We have FPGAs at most places and programmable NICs almost every place. So we also interconnect a lot of national facilities. So national labs, places like NCSA, regional networks, science instruments, to connect all these things, with the ideal being that we want to be able to demonstrate how to ship around compute and storage and data between different facilities. That's called federation, and that's a big part of what we're trying to do. So what this is going to allow you to do is to design and test applications, protocols, and services that run anywhere in the network, not just in different places that are right now, frankly, they're kind of cobbled together. So if you're not used to dealing at scale, maybe some of you, this is like your bread and butter, but if you're not, this is kind of a motivating case for many people. It's an example of a traditional workflow for large scale distributed science. So you have an instrument, you're doing some initial data processing locally, you're storing it locally at a facility. And then you use the network, wide area network, the WAN, you transfer it. And this is why people talk about speeds and fees. And if I just had a higher speed network, I could do more science, more stuff. So you do the data transfer, you send usually to an HPC center for storage. HPC will fetch data from local storage and will start processing. And then there'll be some processing done at HPC. And then it gets put into long-term storage. So this is kind of not for every, obviously, science instrument, but for many, this is your classic model of like collect stuff, send it over the network, it lands someplace, analyze it, and it's there. Older model, not super efficient. So, why is it inefficient? Basically, if the experiments use whatever's available locally to compensate for the lack of kind of reliably schedulable compute resources. Not everything uses HPC. A lot of the high energy physics, they use high throughput computing. There's this, again, talking about cobbling things together, you have the network, then you have your HPC center, the job scheduling time, the real-time compute, it doesn't always match up with what you need. The big thing for us, many of us on Fabric are network people, is the network is often treated just as a black box, especially if you're talking about instruments that are not in the US. If an instrument is somewhere else, you collect your science, you send it over the network, and for many scientists, it's kind of like, okay, I hit go over the network, I'm not sure kind of what happens from there. Part of this, again, is because the internet's terrible, because routing is inefficient, it's unpredictable. Even if you set up your traffic engineering well, that doesn't always work well. So the network as a whole is not super efficient. Access to resources is inconsistent. Different facilities, even HPC facilities and campuses have different security features and federation and allocation policies. And this is where you have this whole ecosystem of people and processes and software just cobbled together to do good science. If that doesn't make sense, I know I went through that very quickly, but that was kind of our motivating factor. As of last year, luckily for us, kind of midway through the project, interconnectivity has become a strategic objective requirement for research and development at the national level. So this is from a committee, And I put this in that this becomes important because these kind of strategic plans and R&D eventually do trickle down into real dollars. So they do influence people's priorities for building out science and infrastructure and where funds go. So this was really important, this shift from kind of the past of going from here to there, these nodes, to a future of much more interconnected, experiments and links and research cyber infrastructure. So at a macro level, this is really important. This integration with the network, this allows this new kind of interaction where, again, having the network as a path and having the ability to do storage and compute along the path, now we can ask what's possible. So we can tailor this for specific workflows and not just have the network as this dumb kind of black box. So going back to Fabric, so we took a detour for, strategically, why do we need this? So Fabric are these 29 nodes, again, one here, big one here at NCSA. 9 are co-located at the Department of Energy's points of presence. So they have in commercial facilities, they have fairly large points of presence with 100 gig fiber and optical DWDM. They're spending this year putting in a new optical system throughout the US. So we're able to leverage that at the very lowest levels, which means there's not a lot of competition for the bandwidth, so you can get straight to optical. And several sites are going to have terabit networking in this phase. And then 20 other nodes are at various kind of regional networks and universities and facilities. So some of the key features of Fabric. So again, the network we see as part of a computing continuum where in theory, anywhere that has a node, any place that's on the network should be able to do processing, machine learning, storage, and not just have it go through there. Many of our sites have dedicated 100 gig optical links. And I haven't talked as much about kind of the computer science, as a science usage, but for computer scientists, the network now, with a facility like Fabric, the network is really, we see it as a scientific instrument in and of itself. So what we've done is all the nodes that are on Fabric, they are instrumented like they themselves are scientific instruments. So each site has GPS, each site has a very fine-grained measurements. So as systems researchers want to collect data, they can do fine-grained measurements to track packets to close to real time, or not quite real time, through the network. And they're able to do measurements to really improve computer science systems. And I'll talk a little bit today, serving a broad range of science domains. If this is if I'm not making sense, please stop me.
I have a question, actually.
Yeah.
How does this bill relate to access and exceed, as they have, their own networking capacity and NSF governs who gets on?
Yeah, so that's a resource that is seen as an operational compute resource where you get an allocation, you use it to compute science, but whereas Fabric is a test bed, but Fabric, I don't think we have plans to connect to access necessarily, but the plan is anywhere where there is an instrument like that, we can in theory federate with. So right now it's mostly with other test beds. There's some production, the difference is NSF doesn't want Fabric, which is a test bed, to be used for production. We don't want people's real science to get affected. What we want to do is test out things for the future real science deployment. So it's kind of a nuance, but we are not technically production. But in theory, we could federate and have traffic go to access. So Topology, started out in the very beginning. A couple of years ago, we developed more, but more. We are right now almost done with phase 2. We only have 4 more sites to go for Fabric in the next year. You can see the yellow is a terabit speed networking, which is very high speed networking and optical. Every place there's a dark blue line, that's 100 gig layer 1, which is also optical. And then layer 2 is the greens. You'll note too, if you're a fan of cloud computing, in 2 places we federate with commercial cloud. And as next week, fairly excited to computer science people, is we will be connecting to the real internet. So that's one of my duties is this test bed is not going to be isolated. In the past, these test beds were kind of isolated amongst themselves. Now, this will be connected to the real internet. So if you're doing some nefarious, I want to test out a command and control bot, you can go out to the real internet. So this is where this isn't kind of a fire and forget test bed. It's there's a lot more care and feeding to making sure we don't take down like the real internet with this test bed.
Nice. Two dumb questions. The L2, is that the outline of you? Is that just showing that everybody has a connection to L2? Or what is L2?
That is an unfortunate color that
Oh.
it,
Oh, I see. The L2 is right up there.
Yeah.
And how come NTSA is in Wisconsin?
another unfortunate artifact of map making. You are not the first person to say that. The New York area people are also.
Well,
very
you know,
upset.
we're
Yeah.
like Michigan, that's better.
They're like, why is Princeton up in, Maine?
Yeah. It's true, over there.
It's an artifact of artifact in map making.
I have a thought question. So this like test bed, let's say, some college student in Illinois is just like doing, watching YouTube or whatever. Would that college student be logged into the test bed without knowing, or is
No, it's segmented.
segmented?
So it's although it runs over that same Internet 2 network, it is segmented. So it has its own IP addresses so that you can only get to it actually through, you have to SSH into it. So it is over the same network, but it's isolated. In fact, many of the people who used our prior incarnation of test beds were students, like 60% of our users were student usage. Our expansion to the EU and to other locations. So this is just to give you an idea of where we're going. When we go to the EU, we're going to be live at CERN in a week. And we're using primarily research and education networks to get there. This is like an eye chart, but these are our partners. The first two networks are funded by NSF. ESN's a DOE network. So we rely on kind of federal, we don't use AT&T or like Verizon to get to these science facilities. We're using science funded networks to get over there. And then we get to the locations, we're using kind of inter-European science networks to run the test bed. Asia Pacific, same thing. We rely a lot on Tokyo has a network called WIDE. So we rely on them. We're possibly expanding to Hawaii, possibly expanding to Guam in the next couple of years. South America, we don't have any nodes yet in South America. So a lot of what we're doing to serve kind of future experiments there, like some of the ones we've been talking about, is a lot of emulation or using other nodes. For example, even for the CERN one, we've used NCSA as like a proxy. So we don't yet have stuff in South America. We do have users there, but they're primarily just, again, figuring out how they would use Fabric until we get a node deployed down there. But these are our network partners to get down to South America. So what is a Fabric node? I won't go into too much detail, but as I said, there's compute, storage, all that are within the rack, and you can actually go and see it in this building if you have data center access. But primarily, like your typical node is this Dell high performance server with some combinations. Some sites have more, some have less of GPUs. Some have FPGAs, some don't, depending on the site, the size of the site. We're very power constrained, so a lot of the sites where we rely on commercial providers, their power is very fixed. FPG programmable network cards for people who are really into P4, which is a programmable networking protocol, and multiple internet interface speeds depending on where you are. Some of the larger sites, and one of the largest sites is Starlight in Chicago, and actually the reason NCSA looked like it was near Chicago is there's a very high-speed connection between NCSA and Starlight in Chicago.
Each of these racks, like 30K, 50K, probably, something like that.
Money-wise?
Yeah.
Oh, like 300K.
Each, wow.
Yeah, the racks up, because then there's a Cisco switch and storage. Yeah, each one
Yeah,
is
okay.
about between 250 and 300K. Yeah, prices have gone up a little bit. And then in addition, there's all the other stuff like intrusion detection and all the other stuff kind of cobbled onto this to provide for things like security research.
But these are almost, from the Fabric point of view, these are almost containerized, or you have
Correct.
and they're all the same.
And actually, they're shipped to Renzi, they're configured, we ship them out, NCSA, they got them in the loading dock, put it together and just kind of, this is just we call the Fabric nodes a hank. It goes with the Fabric theme, which I did not pick, but we have all these, like fabric-ish knitting themes. So Hank is our node. This is what it looks like. Just mostly for reference. The design, some of these slides I'll just kind of blow through, but again, for people who are really into, and some of the science communities are very invested in this, particularly for kind of computer science people, we are instrumented heavily to do measurements. So we do have GPS clocks everywhere to do packet stamping. We have smart PDUs to measure power. We have optical layer measurements. So we are instrumented heavily to do some of the censorship people do the same thing. The ones who are looking at kind of side channel attacks in Tor, that's super fine grained. So they want really fine tuning for the measurement aspect. So again, just another view inside a slice. It's like when you set up your experiment, it's called a slice. So that you only, back to your point about students, you only have visibility to your slice. But we as fabric people have to instrument all of the slices. So it's just another kind of view of that. External connections overview. So again, slices, if you're a student, you want to get a slice to do some crazy stuff. This is isolated, so it's within the fabric infrastructure. You can do whatever you want and try to trash our infrastructure. We're happy to have you do that. Try to push the boundaries. This is isolated from external networks, so you can't hurt very much. So that's kind of intra fabric. We do have the ability for people to use fabric to do, to potentially destroy the internet. But we do these on a case-by-case basis, and they have to tell us why and how they're going to do it. And we monitor that heavily. We do some intrusion detection and all sorts of things. But again, the connections are either, you want to set up a slice, you will have a menu of options, and you can connect to Chameleon, Cloud, or you can connect to different things, and it'll be all set up, and you'll have that. You can do an experiment for as long as you want. I won't go over this too much. This is just to say a lot of the sites have optical connection, including this site here. User interface, again, just a snapshot. We put a lot of thought into doing better user interface than prior test beds. So thankfully, we use Jupyter on notebooks because a lot of people tend to use Jupyter notebooks. We have a user knowledge base. We do integrate with CI logon for federated identity. If you don't know what that means if you're on campus and you have a U of I logon, it's super easy to use Fabric because we federate with that identity service. So that's really good for most universities. That's like a layer that they don't have to worry about. Software overview, I won't go too much on this. This is just to highlight, again, this complexity kind of under the hood. There's a lot of thought put into different software services. So some of our initial beta tester experiments. We had 4 that were Fabric kind of canonical. Here's one in security, here's one in AI. We had a few others kind of come into the fold, but these are our initial beta testers. The reason we brought them in as beta testers is they have interesting use cases that are going to push what we certainly think about Fabric, and use cases that maybe they can't do in traditional test beds. The first one, I should have brought a slide. This is pretty badass. It's Phil Porras at SRI. He's one of the folks that developed Siri. And he's at SRI, and he has this really interesting way of using machine learning and AI across a highly distributed network that they're sensing and defending the network done in near real time. And he uses Fabric to show how to do that. It's really cool. Some other stuff that's cool is anonymization testing. This is where Richard Brooks uses Fabric to test out, again, some of those side channels in Tor to break anonymous. Those of us in security know Tor is not super secure, but he does some proof of this using Fabric as the man in the middle to attack, to show, to prove out how Tor is not secure. So pretty cool smart sensors on the Georgia coast. This is to do some IoT, and what they're trying to do is real-time inferencing on their IoT devices. That's hard to do because they're power constraints, and he's using Fabric to see what they can do for kind of real-time inferencing. I'll talk a little bit about Atlas, and of course, folks here helping us with CMB. And then there's a pretty neat out of NCSA ransomware honeypot that we're deploying, or honeynet we're deploying as well. We have monthly user webinars because people who haven't used test beds is who we're really trying to get to. So monthly basis, we walk people through how to do this. We have a lot of students as well, and our hope is much with Jeannie that this will be used for a lot of classes for students. So some of the science use cases, these are the ones that when we pitched to NSF, NSF's really big on science drivers, and you have to have some relationship or knowledge or a path to working together with the science community, and these are the ones that we pitched. Many of us have worked with Atlas before. We haven't worked with astronomy as much, but we're developing a good relationship. Weather and climate, we have a really interesting use case in Brazil where they're trying to do more real-time coastal sensing and how to these humongous weather sensors and shrink it down so they can alert people, say in North Carolina, that there's going to be a hurricane. Urban sensing, there's a big partnership with the University of Bristol. They have a whole instrument in Smart City in the University of Bristol. There's a similar one in Chicago called the Ray of Things, and we're trying to connect them to do some really cool AI at the edge type things. And then 5G, which is completely not my area, but we're trying to do some, they can stretch 5G networking from Tokyo to Chicago. So that's another big experiment. So I don't know if everybody here is in astronomy or if you're in the HEP community. I am not, but I've worked around this community, and so we have a pretty good relationship with the folks who are on the Atlas project, and they came to us and they have some actual challenge problems. So as you all might know, the current approaches to how data is taken from LHC and how it's processed, these just don't scale well. Used to be went from tier 0 to tier 1 to tier 2, and clearly that's not going to scale very well, particularly with the new run that started this year. So they have been very interested in, and there's been a lot of cyber infrastructure proposals on how do they improve smart delivery of data from CERN and worldwide processing facilities to low latency platforms to do more machine learning along the path. Of course, that's key to quicker discovery. So the way they're going to use Fab, and I'll show a few slides, is they're exploring some data analysis options from CERN tier 0 to the end user processing, looking at how they can employ more machine learning kind of along the way to reduce the data volumes and do data discovery. So this entailed a lot of integration with things like ServiceX, which is a software developed by this Iris HEP Software Institute. They've also used Slate, which is another cyber infrastructure. I didn't list all the stuff, but needless to say, there's a lot of stuff that goes into this processing. So what they did as a test, because we weren't able to get the CERN node up, that won't be up till next week. For the past year, they've actually used NCSA's test fabric node here, but they constructed this analysis pipeline that simulates from Atlas at CERN, filtering, reformatting, and getting to external resources to process, and come right back to a physicist notebook. So here, again, their use case is to get, as of next week, when we get Fab there, they will get Atlas data directly from tier 0, which is at CERN. So they actually, we have a rack that is right there in the CERN data center. They're going to copy the tier 0 data over. They're going to cache it locally. They're going to transform it using ServiceX, and between the fabric node at CERN and the fabric node they're going to use in New York initially to get to, they're going to try to do some machine learning magic along the path. Eventually, they will get to Chameleon, which there's part of it in Chicago, part of it at TAC to do some cloud processing and get to physicists. So at a high level, this is how it looks. You can see CERN, the tier 0 is to the right. So literally, the theory is once they prove out that this is a really great pipeline, in theory, what they will do is then take it back to CERN, take it to the Atlas leadership group and say, hey, Atlas, this is how we should be doing processing from now on. So Fabric is just a way to kind of prove out to the team that this is how it should be done in the future. So they will take data off of tier 0. Purple is the Fabric node, ServiceX, do some machine learning, eventually gets back to the US to do speed, is kind of split, some processing's done, and it gets back to the physicists.
Is the stuff for Atlas actually being used for research, or it's just playing for proof of concept?
Kind of both. Yeah, it primarily, I mean, the primarily is a proof of concept, but it is actually used for real analysis. Yeah.
But the machine learning that we're talking about is focused on moving the data itself and not on the actual data content.
Correct.
Yes.
Yeah. It's how can you reduce it intelligently on the path, that's right. This is just another kind of view of it. So to that point, what this will do is, again, it'll optimize the olds, take everything from tier 0, ship it to a tier 1, ship it to a tier 2, and then that takes so long, and the cyber infrastructure is slow. In theory, this will allow better data to get to people faster. So summary, this took some, getting back to why the internet is terrible. This took some time because CERN and Atlas, being a traditional facility, they don't support IPv6. We as Fabric, of course, most people, computer scientists, are like, it has to be IPv6. That's the future. Well, science does one of these, so we had to kind of work through that. They use Kubernetes. We weren't prepared for that. So some of these are just working through, how do you work with your various communities? But for Fabric, this is the value add for it's not just it's a test bed, take it or leave it. We're trying to work with the science communities to do this demonstration. I'll go to just a couple more. So this is a cool one. This did not come to fruition yet because we had significant supply chain delays. A lot of our equipment is either not commercially available or it's high-speed stuff. So we just had all sorts of delays. We're still waiting for Sienna optical equipment. But in theory, this is a really interesting demonstration that we were going to do with University of Bristol. Again, they have a smart cities lab. When I say lab, the whole city of Bristol is in fact a smart cities lab. So they've instrumented the harbor, the streets, the university. They've instrumented everything to make it a smart city. Similarly, in parts of New York City, there's a test bed called Cosmos. They are built on around what was something called the Harlem Children's Promise Zone. So back about 8 or 9 years ago, there was a section of New York City where they were instrumenting and doing high-speed networking there to help the residents. And that kind of blossomed into a larger effort in New York City. It also blossomed into a couple of test beds, and they just got another smart city test bed. So there's really a lot of cool stuff there. Those people don't talk, the Bristol people and the Cosmos didn't. So we said, what if you guys were able to talk, and University of Miami? And what they were going to do is between the three, using Fabric, we were going to test out some kind of immersive augmented reality, virtual reality deployments, particularly around creative culture, like music and some of these art exhibits, because they had real-time kind of different types of art in the different cities. And so the 3 cities are hopefully next summer going to do this together and kind of co-create some really interesting content. And Fabric, again, for concept, we know that it may not work perfectly, but it's a way to test out some of these new protocols for augmented reality.
And when it's a smart city and you say people are doing things with like what kinds of things?
They are doing things in Bristol like monitoring, and they have some, nascent AI that looks if somebody's gonna. They have a lot of suicides off this one bridge. They're monitoring that to see is that a person who's jumping off a bridge. They're monitoring foot traffic to see, your general kind of pedestrian traffic. They're monitoring, much like the array of things is in Chicago, the environment. So they're instrumenting and saying, is the environment here worse than over there? Is there more smog? So things like that. So they've got cooperation with the city to instrument just a bunch of different things. And obviously, since they're really big on privacy, they're not doing facial recognition, but anything beyond personally identifiable stuff, they can instrument.
I was asking about privacy.
They're much more, that's another tangent, but they're much more aware than we are. So in terms of PII, they are much more ahead. The array of things in Chicago does also some pedestrian stuff. They're not as careful because they don't have to be, but in all of our talks with Bristol, they're like, that is their number one thing. It's if you're going to collect it, you can't store it here. And so yeah, we follow their guidance, which I think is actually really good. Okay, so moving on to CMBS4. This is for improved transient detection. I am not an expert. I'm just the plumber for the cyber infrastructure. But when we put in our proposal, these are some of our goals with your experiment, CMBS4, which is to improve reliability, to improve transient detection, do transient detection in transit, to do alerts in 2 or 3 hours or less. So some of the goals of the cyber infrastructure, again, doing proof of concept for the future, were to improve real-time computing while ensuring reliability, improve latency, and test out potentially the streaming data to multiple sites. So we spent the first few months just, we kind of speak different languages, not only computer science, people, cyber infrastructure, astronomy. Again, many of us had worked with energy physics for years. So just the, I'd say the first 6 or 8 months of just understanding the language of what are you trying to do? What can you do? What should you be able to do? It's this negotiation of, if you're going to do a proof of concept, how do you do it on Fabric? Why do you want to do it? We're here to help you. So that took a little bit of time. I think in the past 2 months or so, there's been a little bit of movement where there's Fabric tests set up at NCSA, some transient detection code was run on the node here. A slice was set up to simulate this path from Chile back to the US to ensure the code can be generalized. And the whole challenge was, can we detect transients using the Fabric software? Can we use this, kind of like to vet ground truth? And is this even applicable? But before we went anywhere else with this, we were helping the team to see, could we even, on events that are already known, kind of ground truth, can Fabric just be used to help do that? And is that going to be accurate? Seemed like it was. Again, I'm just a messenger for this, but working with the folks here, Donald Petrovic, it looks like we are ready to perform, more work for CMV. I think our future goal is, can we help test how to facilitate between alert systems? And much of the experimentation is put on their GitHub site.
So going back to my question about
Yeah.
the energy physics versus this. Here you're actually trying to do machine learning on the data as it comes through the Fabric node itself.
Right.
As opposed to trying to optimize the movement of the lab.
Correct. Yeah, because the challenge for, again, and we rely on the scientists to tell us for HEP, it's like, we can't get bigger pipes, so help us just move the stuff.
Right.
This is a little different, and the same for, I didn't put the slide up, we're working with LSST, but similarly, it's like, how can we get to alert brokers quicker? We rely on really this, the science collaboration to tell us what they need. So that's
Right.
exactly right. Yeah.
Another question on that, like, does it have to be machine learning code or it can be any?
Could be anything. Yeah. And this is all I had for the, I have lots of backup slides, but that's kind of weird. Yeah.
You look back upside down and doing for a purpose.
I do not, because we are in a holding pattern waiting for the right person to talk to. I guess last we talked, there was still a selection process for, I think, the finalists for the brokers. And I think University of Washington might be one. Our next step is wait till we know who those people are and connect with them. So that's really.
Yeah, well, you started your talk with, why the internet hates science, sort of list of things there. I guess my question is, how do you know you won't have some of those same issues with Fabric in 20 or 10 years?
We are 100% gonna have the same issues. And what, so my ideal case is maybe not the same as my collaborators on Fabric. Ideally, really, so we're using this to help science, we're using this to help networking. Ideally, what many of us who are in the networking space want to do is ideally the internet itself, the protocols, the fundamental ways of movement we have to have a difference. So this is going to take 20 years where, for routing, let's say, the way that people do routing right now, for the gateway protocol, you rely on handshakes, you rely on a personal trust, you rely on some cryptographic primitives to do that, but not everybody does it. What we need is ideally in 20 years is brand new protocols. Fabric's a step to encourage people to say, look, if you're just to wipe that slate clean. So the way that computer science people are doing it is they're looking at things like P4, which is if you could just have programmability everywhere, what would you do different? So instead of having your routing as it's done today, you can just completely decouple everything and try it in a new way. So we will for sure have the same exact issues until, again, it's just like you're almost developing in parallel the science, optimization, but also there's got to be a willingness to upend the internet protocols of today and start something fresh. And none of them that have been developed so far have worked. If that makes sense.
Thanks.
Any other questions online?
This is like a potpourri of Fabric stuff. I wasn't sure what folks are interested in. But
No, I think that was a nice overview. We got Yeah, I had the same question. I was curious what exactly LSST or what exactly they were implementing for LSST, but do you know who the contact is on that?
So we're working with William and Leanne. So
Yeah.
we're working with those two, and the use case is fairly similar. It's how can they more quickly get alert streams to the alert brokers? How can they more quickly do that?
Yeah. Okay, so it's upstream of the brokers.
Yes.
Yeah.
Yeah, that is their
Or midstream to the broker and something.
potentially.
Yeah.
That's their number one kind of pain point is we understood it.
Do they, I guess, you have to wait for them to tell you what they actually want to do, as opposed to me sitting here speculating on how to use it.
Yeah,
Yeah.
and that's why we had a couple conversations, because we could tell them what to do, and we have a lot of bright ideas we floated past them, but that's not how they do their science. You know, like there's a couple of folks who have gotten computer science awards. They're like, hey, there's this new type of internet. If we could apply it to LSST, it's like, but that's not how the science workflow goes.
Right.
So that's great, but that's not going to help them.
Yeah, yeah, they want to innovate that. They just want to use what's there.
Right.
But so what are the, so Fabric is like halfway through the MSRI. So what's next? Is there going to be an RFC? Is there going to be a?
So we have one more year of construction, then so that's in 2023. That ends next September, and then we will get a follow-on for operations. So it'll be, I think, either 3 or 4 years to now run production, meaning it's robust, it doesn't go down. We're monitoring it. There's a ticketing system. People can use it for classes, and it's not going down. We're not going to limit. You know, right now it's limited to beta testers. We can kind of handcraft what they need to do. After that, you come in, you want to get an allocation, you know, as long as we're not full, you get it.
Yeah.
So when you're in operations, is it now connected to the internet?
Yeah.
So you have a wider arena where you're drawing, say, use cases from, for.
Yeah, so both, so yeah, I mean, use cases in terms of, so what I'm focused on besides the science use cases is specifically people doing network measurement research. So, you know, like the peering testbed, and there's another midscale that just got set up at UCSD where they're wanting to measure the internet security. They're looking to Fabric as an instrument. How can we work with them? So yes, we're hoping to push the boundaries where, I mean, if you want to see how a command and control bot works, you should be able to get to the internet, but how are we going to control that? So,
Right.
and those are things that people have not done before. So, or they haven't done on the live internet
Do
before.
they foresee, or have they tested to see what will happen if you start trying to use machine learning to defend against attacks? And you at the same time have machine learning on the outside making those attacks?
So that is a space I work in, which is adversarial machine learning.
Yeah.
That's a really interesting question. So yes to both of those, but they haven't necessarily teamed up. I like where you're going with that though, because there's researchers who want, I mean, like now it's everybody and their brothers like, I'm gonna use machine learning for security. But I think that's a great point. If you're also using that to attack, how do you kind of blue red team this? That's actually a great idea. We have people
I don't
independently
know
doing
about a
that.
great idea, but it's obviously what's going to happen.
It's a good research idea though.
Yeah.
You know, where you use a test bed to see how to do this. Yeah.
So for CMBS4 specifically,
Yeah.
Sorry, yeah.
We should go back to science. I'm sorry.
No, that was interesting. But, I mean, obviously, the operation, like, that's not gonna be operational until 7 or something. So how do you view the relationship between Fabric and CMBS4? This is like a use case or a test bed or?
Both. It's, you know, as ideally as CMBS4 is getting ready, if, you know, for example, for this, you know, transient detection, you say, hey, we, instead of trashing production networks, we're using Fabric, and we show that there's a good way to do this. When we get to 2027, whatever, here's what you should be doing instead. So we see ourselves as push the limits, do whatever you want, you know, take down the network, send as much traffic as you can, and then you can see what the boundaries are for real science. That's ideally what we see. And we're hoping to do that for CERN before this run. It's just we got caught up in supply chain stuff. But we were hoping that for this run, they would say, hey, this is a great way, let's actually use it in production. Like that was our ideal use case.
So LSST, you end up servicing multiple brokers, is there a concern about duplicate effort if you end up doing that transient detection, for example, upstream while sending the streams in multiple different directions?
I think that's something we would want to push the boundary of. I mean, we as computer science or test bedding people would love to see that. And see maybe, work with LSST to see, well, what's the impact then? I think again, I say we're just the plumbers, but really we're just the cyber infrastructure people. I think that could be a really interesting test and say on the other end, what does that mean in terms of duplicate processing, or you find something twice, or, we are there to help the LSST science people figure that out. That makes sense.
Going back to CNBS4, like, are there any plans to link up to the satellites, since there's like South Pole, we don't have a fiber network? What's your lowest speed that you can work at?
Our lowest speed, we can work at anything. It's interesting to say that because, NSF for years has tried to get to the Antarctic or try to get to different places. Right now, in terms of nodes, we're hoping to get to places like Hawaii and Guam, and we can go as low speed as we need to. We're trying to get as close to Antarctica as we can. We're trying to get to places where people don't have connectivity that's great yet. That's just been tough.
So hops to something like New Zealand or something like that, in between.
So we talk to them all the time, and that's like, yeah, we have a very good relationship with Rayons and the different people in New Zealand. And it's getting easier to get there for cyber infrastructure. That's actually our ideal next place to go. But you're right on the mark.
Any other questions?
Sorry, it wasn't as astronomy and astrophysics focused.
No, it wasn't intended. That was a question. Any last call for questions online? Okay, let's thank our speaker again.
Machine learning and type machine learning, it's kind of like